Unit 2 is about atoms and their structure. So we're going to talk about the pieces of atoms, where they're at, how we know that. Okay. And we got to start with something basic. How do we know there's atoms? Because we're never going to see one. We're going to talk about atoms all year long and never see one. We're going to draw pictures all year long and never see the thing we're drawing pictures of. Okay? Kind of strange. Okay. But along the way, hopefully you'll notice that those pieces that we talked about last chapter, the laws and the theories, you'll see them working the way they're supposed to. So today, we'll talk about some laws that led to a theory. And then later on, we'll see how that theory had to be changed because of new information. But first, we're going to start with a little history lesson. So, the history of the atom. Let me give you the history of the atom. About 14 billion years ago, Big Bang started the universe. There were atoms. They were all hydrogen atoms. Eventually, some of them turned into other atoms. That's the history of the atom. Okay, that's not what we're studying. We're studying the history of the idea of the atom as a theory. How did people come up with the idea that there's atoms? So how did people come up with the idea that there had to be atoms? The idea came out of ancient Greece. 400 BC, the golden age of Greece. Anybody talks about ancient Greece and how wonderful it was, this is the time they're talking about. This was when they're at their peak. Okay. Lots of ideas came out of early Greece, got adopted. Okay, so in ancient Greece, there were two philosophers. Democritus and Leucippus are given credit. They were both heads of a school of philosophy. Okay. We had a bunch of people they were teaching their philosophy to, followers, people who believed their philosophy was the way to live their life and how the world worked. I was very careful to use the word philosopher here. It's because they weren't scientists. And they couldn't be scientists because science hadn't been invented yet. At this time, you didn't look at the world to figure out what was happening, because the world could lie to you. That you got to the truth through logical argument. That's how you got the truth, was through logic. Inside your head, everything's perfect. Out in the world, everything's flawed. So how can you learn anything from a flawed world? So they didn't look at the world at all. They didn't experiment the way others did. So here's what they did. They looked at a beach. You say, hey, a beach, well, what makes a beach? Well, beach is made up of little pieces of sand. So I can make something miles long out of little tiny pieces. That's pretty impressive, isn't it? Little pieces can make something miles long. But then, if I take one of those pieces and crush it or cut it, all I get is smaller pieces of sand. That's the limit of how they use the universe in their solving of the problems. Because then they do what philosophers do. And I want a philosopher's job because it's great. You get to ask the questions, then you answer them. You get to pick which questions you want to answer. And their question was, is there a piece of sand so small that you can't cut it and still have sand? That's the question they asked themselves. Is there a smallest possible piece of sand? And if you cut it, it's no longer sand. And being philosophers, they said, It only makes sense there must be. And they called that little piece of sand atomos, which is Greek for not to be cut. The root word tome is cut. Prefix a in front of it means the opposite, not to be cut. It's just like our literal translation is indivisible. Divisible is cut. In means not to be, right? Indivisible. Okay? So we have an indivisible atom. How did they arrive at that? They thought about it. How many people ever heard of Democritus and Leucippus before you read last night? Okay? That's not surprising. Because there was another Greek at the same time. You might have heard of him. His name was Aristotle. Anybody heard of Aristotle before? Yeah, so Aristotle was famous now. He was famous then too. Well, not famous, well known. He was the head of a different school of philosophy. Aristotle's school of philosophy believed in continuums, that there was a wide range that things could be. Okay? So that the world was made up of just 4 elements, but they're not elements the way we think of them as elements. Aristotle's 4 elements were fire, air, earth, and water. That everything in the universe was made up of those 4 elements blended in different proportions. That to Aristotle, water was the liquid stuff. But if you added fire and air to it, you turned it into steam, which was something completely different. That you can make every substance by blending those 4 components in different parts. Things that were fire were hot, they were shiny. Things with air were light and cool. Things with earth were heavy and cool. Okay? So to make steam, I have to put fire and air into water. I need the heat and the air. And water was wet. Made things wet, made things liquid. Okay? You just blend them in different proportions to get everything else. So everything was made up of those 4 portions. Well, if you can blend in any proportion, then you don't have any chunks. Because you can't add fractions of pieces if you got chunks. So Democritus's idea and Aristotle's ideas clash, which is okay because their philosophies clash too. Democritus' philosophy was about particles, individual pieces. Aristotle's philosophy was about continuums. They disagreed about everything. So, who was right? Well, the answer is neither one of them. But what's important is how did they decide who was right? Because they didn't experiment. The earth will lie to you. You can't trust your senses. How do you get to the truth? You get to the truth through debate. Okay? They settled by argument. It was a debate. And it took place in the amphitheater. People would come and watch days of debate. There was no TV. And it was a very formal debate called the rhetoric. There's a very formal structure to it. So people would come and try to decide between these 2 philosophies as they argued in front of each other. Okay? So, who do you think won? Who had you heard of before? Aristotle. Yeah, Aristotle won. He won that argument. And the ideas of Democritus and Leucippus went away for a while. And Aristotle's idea got picked up, most importantly, by the early Christian church. Okay? And his ideas carried all the way through the Middle Ages. In fact, not believing in Aristotle's idea was heresy. That the church picked up his ideas in politics, in justice, in ethics, and in science. The science was wrong, but that doesn't mean you'd be a heretic if you argued against it. Okay? The people that did science-like stuff in this area, in this time, they weren't called chemists, they were called alchemists. They're not called chemists because they weren't using science. They were using Aristotle's ideas, Aristotle's philosophy. And when I picture an alchemist, I picture Merlin from King Arthur. Okay? They worked with a lot of the same glassware. In fact, they designed the glassware a lot of chemists use. They came up with a lot of techniques that chemists use, but they weren't doing chemistry. And one of the things they're famous for is trying to turn lead into gold. Because, they must have been crazy. No, they're not crazy. If Aristotle's right, you should be able to turn lead into gold. Because lead is very dense. It's almost all earth. Gold is also very dense, but it's yellow and shiny. So it's got some fire in it. So if you can just get a way to get the fire to stick to the lead, to stick to the earth, you can turn lead into gold. They weren't crazy. They were just wrong. Their logic said they should be able to turn lead into gold. And it didn't help. Lead, when you start doing chemical reactions with it, makes a lot of yellow compounds. So when lead starts turning yellow, you get really hopeful. But it never turned shiny and yellow. Okay? They weren't crazy. They were just wrong. Okay? Because they weren't doing science. Okay, they weren't doing science. Who's next? Your book skips a few people. Okay? Science got invented in the late 1600s. Okay? And the first scientist that we really talk about in development in your book is John Dalton. Late 1700s, about the time of the American Revolution. So that's a little jump from 400 BC to late 1700s. Little 2,200 year jump. Okay. They said teacher in your book, but you got to think about what teachers were like in the late 1700s. They didn't go to school. It was more of a private tutor. A family or families would hire somebody to teach their kids. You and your neighbors get together. You teach all the kids in the two families. It was a private tutor. But the key is in the late 1700s, we finally had good, reliable mail and printing. So Dalton could write letters to anybody in Europe and expect a response. So they could share data with letters. Or you could print books with your data in it. What also had happened is in the late 1600s, they changed the definition of element. They knew Aristotle was wrong. So they changed the definition of element to something that couldn't be broken down any simpler. So the way you found an element was you took something and you did not know what it was. It might be an element. So you do all sorts of chemical tricks to try to tear it into smaller pieces. You tear it into smaller pieces. If you know what those pieces are, they're uninteresting, throw them away. If you don't know what they are, they might still be an element, try to tear it apart. If you tear it apart into smaller pieces, you know what the pieces are, throw them away. The pieces you don't know, you try to tear them apart. Eventually you'll get to a point where you can't tear it apart anymore. That makes it an element. They're just trying to make it simpler and simpler, tearing it apart. We should make it lighter and lighter because you're getting rid of pieces all the time. So they changed the definition of element. And because he was sharing lots of people's data, he could see patterns in that data, and he came up with several laws. One of the laws is the law of conservation of mass. What's a semester? Okay. Studied the law of conservation of mass in the past. That is, mass can't be created or destroyed. In looking at all the experiments other people were doing, he found that the mass before they started was the same as the mass when they ended. Okay? Then he found the law of definite proportion. Okay? Definite, certain proportion, ratio. Law of definite proportion means that there's a certain ratio in that compound. That no matter how much you have, no matter where you get it, the ratio of the elements by mass is always the same. For example, in water, the oxygen always weighs 8 times as much as the hydrogen. So if I have 2 grams of oxygen, if I have 2 grams of hydrogen, I know there's 16 grams of oxygen. It's always 8 to 1. No matter how much water you tear apart, no matter where you get the water from, it's always a specific ratio. It doesn't have to be a whole number ratio, but it's got to be specific. It doesn't change from compound to compound. So what he saw was a whole bunch of data about people trying to find new elements by tearing things apart. And when they found those elements, he found that the elements ratio was the same no matter who did the experiment or how much stuff they did. So compounds always got put together with the same weights. And then after doing some further data analysis, he came up with a different pattern, the law of multiple proportions. It starts off with a caveat. It only works in a certain situation. 2 elements, more than 1 compound. So sometimes hydrogen and oxygen make water. Sometimes hydrogen and oxygen make hydrogen peroxide. Think about all the things in biology last year that were just carbon, hydrogen, and oxygen. Those 3 elements can make lots of compounds. Right? There was a bunch of them, weren't there? Okay. So if you've got more than 1 compound, you want to take a ratio of the stuff in parentheses. The mass of the second element that can be combined with 1 gram of first. That is the mass of the second element over the mass of the first. So it's saying take a ratio of this ratio for the 2 compounds. So you find the definite proportion for the first compound, you find the definite proportion for the second compound, and then you find the ratio of those ratios. And every time you do that, you get small whole numbers. Your ratio is a small whole number. 2 to 1, 3 to 2, 3 to 1. No matter, it happened everywhere. So that the ratio of the ratio, so I take 1 ratio for each compound, and then I take a ratio of those ratios. And every time I do that, I get a whole number ratio. It's complicated to write. I can't imagine how he came up with it. That means that's what he did, was he compared compounds to each other on a whole bunch of different places. Okay, so we said water has 8 grams of oxygen per gram of hydrogen. If you tear hydrogen peroxide apart, it's 16 grams of oxygen for every gram of hydrogen. And if I take a ratio of that 16 and that 8, I get a whole number ratio, 2 to 1. If I'd done it upside down, I would have gotten 1 over 2, half. But you always get a whole number ratio. It's never some random decimal place. It's always a whole number ratio. That the ratio of the ratio is a whole number ratio. The ratio of the ratios is a whole number ratio. They call it multiple proportions because you're taking a ratio of a ratio. That's why they call it multiples. First you take a ratio, then you take a ratio of those ratios. So the ratio of the ratios is a whole number ratio. So he saw those three patterns in the data. Okay. Always worked out. He asked himself the logical question: why? Why is mass conserved? Why is the compound always the same ratio? Why are two compounds always in whole number ratios? And the answer he came up with, the only possible way he can explain that, is that there's atoms. Atoms explain all of those pieces. How do atoms explain that mass is conserved? How does atoms explain why mass is conserved? That the things that you start off weigh the same, things you end up with weigh the same as the things you started off with. How do atoms explain that? Well, what did Dalton say about atoms? Said they can't be created or destroyed. If they can't be created or destroyed, every one I start with has to be there at the end. So if I weigh them at the start and I weigh them at the end, they're going to weigh the same. Atoms explain the law of conservation. Atoms are an idea that explains something. Atoms are a theory. He hadn't seen an atom, but he knew atoms were there because mass was conserved. He knew atoms were there because of the law of definite proportion. Why do you always get the same ratio? Because an individual atom of oxygen is heavier than an individual atom of hydrogen. But as long as I put those two together, the ratio is going to stay the same. Because oxygen always weighs what oxygen weighs, and hydrogen always weighs what hydrogen weighs. That's what we're talking about in terms of laws and theories. The laws come first. They see the pattern. They tried to explain it. The only explanation they got is atoms. A few questions tonight?